Let us have a recap of the previous topic. In the previous topic, we have developed our understanding on the CPU compute node and GPU compute node, as well as the computing device which are used for the computation. And we have seen that in any computing node there is a two computing units, CPU and GPU, and CPUs can be multi-core CPU and there can be multiple GPU cards on a single motherboard. But apart from this hardware, the efficiency of the compute node also depends on the operating systems, or you can say various software stack. So, in this topic I am going to discuss about the GPU software stack, which basically makes the entire GPU functional for any application to execute on. The software stack is basically the hierarchical component. You can say it is a layer wise structure. It is placed between the user application and the hardware. So, you can see that layer I have mentioned CPU and GPU. These are two computing devices over which another layer has been added, that is operating system. Above operating system, another layer is known as device drivers has been added. Over device driver, some libraries and compilers has been added, and over it the various programming models which are required to program the underlying infrastructure. Above all of above there is an application model, or you can say application layer. User can develop their applications considering all these layers for the underlying infrastructure. So, basically in simple terms we can understand the software stack enables the efficient execution of parallel computation on GPU or CPU. So, let us discuss layer one by one in detail from bottom to top approach. Apart from hardware, the first layer is operating system. It manages the hardware resources, it provides essential services like memory management, input output operation, process scheduling, and it also establishes the interaction with the device driver to ensure the allocation of GPU resources to the application. After the installation of operating system on a compute server, device drivers are installed. Device drivers is a kind of software that is hardware specific. It always serves as a bridge between hardware and software, and it manages the low level tasks such as memory allocation, thread scheduling and kernel execution with the help of operating system on the underlying hardware. Once we make the device driver functional, we need to add few more softwares. We call it compilers and libraries. As you have an idea of the compilers, compilers basically translate the high level application code into the machine instruction, and similarly there are various libraries are available for different activities Just like I can take example of BLAST library, Open BLAST library. So, these libraries are the optimized implementation of some commonly and widely used functions. Above that, there is a programming model. Understanding of programming model is very important in a developer point of view, because programming model gives the abstracted view of the complex hardware to the user and make it easier for the developer to focus on the parallelization rather than thinking about the underlying hardware architecture complexities. So, such programming models, there are many programming models are available for different hardware and for different needs, just like CUDA, HIP and OpenMP, MPI, etc. All of the above, there is a application layer. Developer there develops their application using the programming model, and while developing the applications, user have to think about how he can take advantage of the parallel processing capabilities either of CPU or GPU, because application development is totally relying on the programming model and libraries to efficiently distribute the computation across the computing devices, or you can say in terms of GPU, many core of the GPUs. Now, let us discuss about the host device connectivity. As we have seen that in a compute node, especially the GPU compute node, there is CPUs are available on the board. Additionally, GPU cards has been added, and these cards are placed on the PCI slot, and GPU card always has to travel or communicate with the CPU to GPU with the help of PCIe interface. In any GPU compute node, the CPU and its host CPU memory. In a host device connectivity, you can see that there is a host. Host means the CPU and its own memory is known as a host system, and additional card that has been added on the same board or same node, that is known as device, or you can say GPU card. So, that is the reason we always have to remember whenever we are working on a heterogeneous compute node where CPU and GPU both are available, the CPU is always known as a host system and GPU is always called as a device. Here I just given some illustrations of different GPUs from different vendors which widely used in scientific and engineering simulations. So, first one is from Nvidia, the second one is from AMD, and third one is from Intel, and all these cards are placed on PCI slots, or they can, each vendor can might have provided their own vendor specific links to connect GPU to GPU and GPU to CPU. Let us discuss the anatomy of GPUs. Here I am going to cover two GPUs, Nvidia and Intel. In anatomy means we want to learn about the various components that are present on the GPU card. Let us discuss first the Nvidia GPU architecture. This architecture I have taken from the white paper that is published by Nvidia on their website. Here I want to tell you about the organization of compute cores on the GPU. If you are able to see, these blocks. This is a one block. Similarly, this is a second block, this is a third block, this is a fourth block, similarly fifth and sixth block. Means at very high level in Nvidia GPU, cores are arranged somehow like these 6 blocks in a particularly chosen GPU, and this number of blocks can vary. But what is the name of these blocks? That is known as graphic processing cluster. Within that, now I just get inside of each GPC, in short we are calling it GPC. So, we can see that there are some blocks are mentioned like this, some blocks are mentioned like this. This blocks is known as TPC. Let us count how many TPs are present in a single GPC. So, this is 1, 2, 3, 4, 5, 6 and 7. So, that means there are 7 TPCs are present in a single GPC. Further, I will dig into the TPC later on, but before that I will discuss few more components that are present on the card. Here you can see there is a memory HBM. The 4 memory chips are available on the GPU card, that is called HBM2. Apart from that, you can see there is a PCIe 3 host interface. So, this is a PCI connector is available. At last, you can see this green color boxes. So, there are 6 NVLink. These NVLinks provide mesh connectivity among the GPUs. Now, let us focus on inside the TPC. So far we have focused on GPC at high level, and the next high level is TPC that you can see here. This is a TPC. Now, we will look inside the TPC. What is inside the TPC? So, if we look inside the TPC, you can see that there are divided into 2 sections, and these 2 sections is known as SM, streaming multiprocessor. So, you can say that per TPC there are 2 streaming multiprocessors per TPC, and here I have just shown the enlarged view of one SM. So, let us discuss the streaming multiprocessor detailings. This is the main section where actual compute cores are exist. Here you can see that at top there is a L1 instruction cache. Within that again there are some blocks kind of structures are available, you can see here. So, within a SM the actual compute cores are further arranged into some blocks. So, there are 4 blocks, and these 4 blocks are known as process block. These 4 blocks are known as process blocks per SM. And apart from these 4 blocks, here you can see there is a L1 data cache and shared memory that is present in each SM. So, now I will get into the each process blocks in detail. Before that, I will just give you the purpose of L1 instruction cache, process block and L1 data cache. So, L1 instruction cache, as you know the name suggests, it is a cache cache which is provide the cache functionality, and okay. So, L1 cache provide the cache functionality. It is for instructions. It serves as a critical function to store the frequently used instruction locally within the SM. The primary goal is to minimize the latency when fetching these instructions. It basically ensures the necessary instructions are already available nearby, and this proximity dramatically reduces the time it takes to retrieve the instructions from the memory. Process block, this is the heart of the SM. As we have seen that there are 4 blocks, process blocks in each SM, and these process blocks basically contains the multiple cores that can handle the variety of data types and precision levels such as FP64 double precision, FP32 single precision and int32, and it also enables the wide range of mathematical operations. This process blocks is basically managed by the warp scheduler, and it can execute multiple warps in parallel. The main objective is to enhance the overall throughput. Alongside these cores, the other components such as the warp scheduler, instruction dispatcher units and data cache work together to maintain the smooth and optimized processing within a SM. L1 data cache and shared memory. So, it basically stores the data, just like we have discussed about L1 instruction cache. It is related to the instruction cache, or you can say it is related to the instruction. Similarly, there is a L1 data cache or shared memory. So, this memory is related to the data. It stores the frequently accessed data that the threads within a warp requires, and it significantly reduces the latency associated with fetching the data from the global memory and making memory operations much faster. It allows for the efficient inter-thread communication and minimize the memory access bottlenecks. It is particularly useful in scenarios where multiple threads need access to same data, such as matrix multiplication or reduction algorithm. Let us get into the detailing of each process block. So, you can see the organization of the process block. So, there is a L0 instruction cache. Within that, after that there is a warp scheduler. Warp scheduler can handle up to 32 threads per clock cycle only. After that, there is another component, that is a dispatch unit. Dispatch unit basically decodes the instruction and send it to the appropriate function units. Register files. So, you can see that register files, it is around 384 registers, and each register is of 32 bit. After that, you can see this section, this entire section is representing the compute cores, the actual compute cores. So, you can see that there is a compute core is of int type, this is a float type, and similarly FP64 is of 64 bit, and it is only of 8 such 64 units are present in each process block. Apart from that, you can see that there is this unit at last, load and store unit, that basically fetch the data from the memory and load it to the register files. At last, there is a SFU unit, special function unit. So, any mathematical special functions as like square matrix kind of trigonometric kind of operations can be performed by this special function unit. So, here is the detailing of these each components. L0 instruction cache, this cache is very much close to the actual compute units within a process block and stores the most recently used instructions and keep the instructions close to the execution unit and rapid instruction retrieval. Next unit was a warp scheduler, as I discussed, is manage the execution order of the warps and decide which warps to execute next based on the available resources and the data dependency. Suppose there are 5 warps are available and out of 5 warps only 3 warps that are ready with all the data, then warp scheduler can take a call to schedule any of the 3 to the resources. It always try to keep the GPU execution units fully occupied and minimize the idle time. Dispatch unit basically works closely with the warp scheduler and assigns instruction to the appropriate execution units once the warp scheduler selects a warp. Suppose data is not available in the nearby cache or nearby registers, and then dispatch unit will send the instructions to the load and store units, and it will ask to the load and store units bring the data from the memory into the register file. So, basically it always ensures the distribution of instructions to execution units based on the data types currently to be executed, like FP32, FP64, int32 or tensor core, etc. Register file, it is also a storage space, as you know that each computation unit works closely with the register files. So, the compute unit which wants to do the computation on any data, that data should always be stored in the register space. It allows the threads to access the data quickly without going to the slower memory level like global memory, ensuring the minimal latency during the execution. Next is computation unit. So, there are 3 or we will say 4 type of computation units are available: FP32 computation unit, FP64, int32 and tensor cores. These core execution units handle the actual computations and performs various type of arithmetic operations. It allows to handle a wide range of workload from the graphics, rendering to scientific computations and machine learning. Load and store units, as I already discussed, its functionality of storing the data from the global memory, shared memory or local memory to the register file. And ultimate aim of the load and store unit is to provide reduced memory latency. Special function unit handles the complex mathematical operations such as trigonometric operation, logarithmic operations, matrix exponential operations, square operations, etc. Whenever such kind of operation is detected in a program, dispatch unit sends those instructions, or you can say offload those specialized tasks from the general purpose compute units to specialized function unit. Before proceeding further, it is always important to know that the number of GPUs, number of process blocks within a SM, number of cores, FP32 cores, FP64 cores, they can vary from GPU microarchitecture to architecture. So, it is always important whenever you are dealing with any microarchitecture to refer the particular architecture data sheet for detailed understanding. Thank you.